training error, test error. Right? Today the task is relatively simple. We don't have a high-level new messages to talk about, but we have let's go to the low level, the coding part. Right? So today we are going to talk about one of the simplest and the useless tool, K-nearest neighbor. So I choose to cover this not because it is useful. It's really because it's simple. It only has one parameter to control, and that parameter actually nicely corresponds to the complexity we were talking about. So last time there was a big question, when we talk about complexity, what do we really mean? Right? So this time we will see when this parameter goes from small to large, the model actually goes from more complex to less complex. Right? So this is a nice, simple tool, easy to understand, and we are going to use that to illustrate that the idea of this is the trade-off. Right? And that's the main thing for today. And before that, I will spend an hour or so on simulating data, some of the fundamentals, just to make sure you can do the homework for today. Right? So last time we talked about a lot of the irrelevant things, but this is the most important picture I mentioned. This is the most important message in this whole course. We talk about, you see I have a new pointer that works on both sides. Last time I found that the video focused on one of the screen and doesn't capture the pointer. So I get a new one. So last time we talked about this trade-off, right? We talk about what is the training error, what is a test error, and training error goes down when your model becomes more and more complex, and test error is a U-shaped. We'll have an underfitting, overfitting. And further we talk about the test error, which is the main thing we want to focus on, can be decomposed into the summation of three components: bias, variance, and the irreducible error. That's a decomposition. And that's the main thing. But before moving on to today's topic, there was something I want to clarify, probably not so clear. So last time we talked about several concepts of errors. And number one thing we talked about was the training error, right? We know training error. We have a data sample that the data set we use to train our model. We call that training model. Right? So there's a data set for training, and after training we have some sort of an algorithm. We can measure that error in the training data set. Right? You have a data set, you know the true y of those data points. You can apply your algorithm to predict the y. Then you can compare the prediction with the true value. You can measure the error. Right? And there's another word we have been using, that's the in-sample error. So that's the same thing here. So basically, this is the error we measured in the same data sample we train our model. Right? We said that's meaningless, but there are two ways of talking about that: training error and in-sample error. That's the same thing. So the thing I want to clarify is on the other side, we have been talking about test error and the out-of-sample error. These two are not exactly the same thing. Let me clarify. So first, the test error. So when we trained an algorithm, we find a way, approximation to the function f. So we want to test how good our understanding about this thing is. So the standard way is we get another data set that is different. We said we want to make sure that the exam questions are not overlapping with the exercise question. Right? So this is another data sample. And we measure our error on that side. So that is the test error. Right? And we say what we should focus on is test error, the training error, meaningless. Right? But the one thing I forgot to mention is that test error itself is not the ultimate thing. The ultimate thing is at the top. we're talking about the population. We're talking about we want to measure the salary of some graduates from a program. We measure their income, the seniority, all these things we want to predict. Right? So there's a general population back there, and in practice we cannot. We assume the population is large enough. We cannot really measure our understanding really at the population level. Instead, we take a small test sample. Right? So both training data and test data are just one random sample of data points that is coming from the underlying common population. Right? So the real thing we really want to say is actually the error we want to talk about is the out-of-sample error. The out-of-sample error is measured on the population. That is the ultimate thing we want. So by looking at the training data, by building up some function to approximate the f, at the end of the day, we hope that our understanding can be measured at the population level with the smallest possible out-of-sample error. Right? But this thing, just like the population, exists in theory. In practice, you can never measure all the whole population, just too many of them. And in practice, you will never be able to measure the out-of-sample error in any way. Right? So in practice, what we do, we get another sample. There's a test error. We measure the test. Right? But roughly, test error and the out-of-sample error are not exactly the same thing. Right? They are measured on different places. And this is the whole thing, but in practice, it doesn't work. So we use that to approximate. So this is an approximation. Right? So we can always measure a test error. So we can say the test error safely approximates the general error in the population if the test data is large enough. Right? So naturally, you can see last time we emphasized that the training data itself is random. Therefore, whatever model we build based on that data is random. So everything derived from this training data is random. Now we are deriving some other error measure from a test sample, and test sample itself is a random draw from the population. So the test error itself is also random. And today we are going to see there are two types of randomness happening at the same time that creates a lot of issues. Right? That's just because at the back end it's not feasible for us to get a comprehensive understanding of the out-of-sample error at the population level. So that's the practical constraint. Right? Is this clear or anything? All right, good. Later we will see there are many other sources of randomness. So today we'll experience this too. Right? There's some randomness driven by the random training sample, some randomness driven by the random test sample. Some of the algorithm might perform badly in terms of a test error. And it's very hard to say, is that because that's a bad algorithm? We didn't train really well? Or it's because the test sample is random, so it's just unlucky. You get a bad test error. Okay? That's the two things are kind of involved. All right. So I shouldn't move less. Simulation. Right? First part of today's stuff, simulation. Yeah, I messed up the animation. But when we talk about simulation, we're talking about why are we doing that and how we're doing that. Right? So why do we do simulation? Last time we briefly mentioned that. Right? We said in practice, the population is controlled by somebody else. We don't know how the population behaves. We believe there's an F. We get some data. We're trying to guess what's the underlying F out there. And we said, but the good thing is when we do simulation, we can play the two roles at the same time. We can first design a population with some known F out there, and we can simulate data samples from that population. That's the first role. That is generating data just plays the role of the God. Then the second part of the role is now we assume we don't really know the population. We only have the data sample. We apply our learning mechanism and trying to say something about the underlying unknown F. So at the end, we can compare the true F we know from the first row and the estimated F we learned from the second row. And by comparing these things, we can tell, are we doing the right thing? Are we doing the good learning procedures? Right? So in order to play the first row, we really need to have a solid understanding about how do we really simulate data and generate data. Right? That's the first part of today's topic. And when, in terms of how to do that, there are two parts. The first part is really what should be this F in your mind. Right? You can make a really simple F, a straight line, depends on 1 of X. Right? That's up to you. Or you can make a super complicated F. Later I'll show you a very complicated F. So how do we design some kind of a structure? And it depends on really what you want to tell. You want to see if this tool is good for low dimensions or high dimensions. Then you need to simulate really high dimensional, many X. Right? You want to tell whether this tool is good for linear or non-linear. You can simulate a straight line and simulate some curved lines and test different things. Right? This really depends on the needs and what you want to understand. So that's the first is a stochastic model. And inside the stochastic model, you have a function F. This function F depends on some input X, and there's some noise. And you need to generate each individual component of this function. Right? How do you generate noise? What should be the distribution of the noise? You have 2X. How do we get this 2X? We need to come up with this number. Right? So that is the next level. How do we simulate each individual component in this function? Yeah, that's what I'm trying to say. Right? There are 2 levels of that. So let's do some simple exercises, just some illustration of what do we do in practice. And this whole process is a so-called Monte Carlo simulation. So Monte Carlo is a fancy name. It doesn't mean anything extra. It's just, in practice, there are many types of simulation. You can simulate driving an F1 car. You simulate the physics, dynamics of these things. Right? That's simulation, physical simulation. Well, what we do here is we are simulating the randomness, the probabilistic context, and the environment. Right? So we're simulating the probability and the randomness, all these things. So this is, as long as you're simulating the probability stuff, this is the so-called Monte Carlo simulation. Right? And Monte Carlo starts from the casino stuff. And in the very old days, people simulate using computers to simulate this Russian roulette, all these things. Right? That's Monte Carlo. Yeah, so that's not the important thing. And I have mentioned that the whole point is not really to generate some number for fun. So we want to really compare the true F and the one we have learned. And we want to know the pros and cons of that. And that's also part of the homework today. We would design some simulation to understand some weakness of some tool. Right? So this is the details. Right? How do we do these things? We need to go from the really bottom level, where we talk about simulating the noise, simulating the randomness. We need to talk about the probabilities, the distributions. How do we govern all this randomness? Right? So I have listed the commonly used kind of distributions. Later I'll show you how to do that. There's a document. But before that, I assume you have seen all these distributions. let me first talk about random sampling. We'll do a lot of random sampling later, not even in the simulation context. Later we'll say we have a big data set, we need to split that into two. How do we do that? We randomly take 50% of the points to the side. Right? That's a random sampling. That's going to be rely on some code here. We're going to. And the other things are just distributions, right? And those probability distributions are, don't worry about the underlying math. But the really important thing is you need to know what's the best situation to use which distributions, right? Normal distribution, let's say, when we talk about normal distribution, when do we use normal distribution in a random context? When do we use that? Large population. And then anything else? There's a mean, there's an average you need to know, you need to specify. Right? But let's think about, that's one step further. Let's first think about when you need to simulate something, like I really need to simulate the color of these data points. It takes two colors, red and green. Can I use normal distribution? No, the output of normal distribution is continuous from minus infinity to positive infinity, right? So that's the first thing to check. That's the easy thing to check, right? Normal goes from minus infinity to infinity, and that's a continuous number. If you need a count, how many goals, you need to simulate how many goals in a football game. You don't use normal distribution, right? That doesn't work that way. The next step, that's what you would talk about. Normal distribution is sort of a bell-shaped thing. There's some area is more likely to happen. There's some tail area is less likely to happen, right? And the bell is centered around its mean, and the side, the range is governed by the sigma square, that's the variance. Right? That's pretty much all you need to know, right? If you are comfortably kind of confident to say, yeah, I roughly know it's going to show up in this range, right? So the most common thing we use for normal distribution is a noise, right? We want to generate some noise. How do we generate some noise? Noise is something just fluctuating, right? On average, noise just cancel out. It has a mean being 0, but it just fluctuates, right? So that's the good thing for noise. Uniform. Uniform can be anywhere. Uniform, later you will see, we do a lot of uniform for our x. So when you say f is some linear function of x, and you need to simulate x, give me some x so that I can calculate. But how do we specify x? There's no particular rule. So we just say, all right, x is from 0 to 1, equally likely. So there's no particular reason to have any differentiation. Right? So uniform is like we write like from minimum to maximum. You just need to specify a range. Right? X is okay from 0 to 1, and equally likely, doesn't differentiate at any point. Right? And Poisson and binomial are just discrete things. Poisson is for count that goes from 0, 1, 2, all the way to infinity. So you want to model some arrival of customers and all these things. There's a count, integers. And non-negative, so you have to use that. Normal doesn't work there. Right? Binomial, we don't really use binomial in practice, but because binomial is approximately Poisson in some sense, and it's much easier to use Poisson. But yeah, let's forget about that. That's not important. Multivariate normal is critical because today's example is about multivariate normal, right? So when we say normal is just one variable, it has its own fluctuations. It has a center, that's the mean, it goes left and right, right? Roughly that's the range. When we say multivariate normal, it's just two normals, right? Think about the stock price of Google and the stock price of Apple. They both fluctuate up and down, right? If they are not related, then you just use two normal random variables. You can solve the problem. But the issue is these two guys fluctuate at the same time, right? Most likely when you see Google goes up and Apple goes up, right? Their fluctuations are related in some sense, right? So how do we model that relation? And you need two x and x1 and x2, and you need your x1, x2 to be fluctuating in a coordinated way, right? How do we do that? And that's multivariate normal. So think about this is price for Google. This is price for Apple, right? If you go to the history every day, you check the price of these two things, and that's one data point on this two-dimensional plane. And if you check the data point, it's roughly like that, right? When you see a high price of Google, you tend to see a high price of Apple. Well, it's not exact. It's not like a fixed linear function. There's still some randomness. They have their own randomness, right? So when we have to model things like that, we say, yeah, this thing is roughly, if you plot a histogram on the two-dimensional, right? So let me put it here. So when you have one normal variable, you can do a histogram. When you have a data, you can do a histogram like that, right? And that's approximately the value. It's just count the frequency. And when you have a bivariate, this is with two dimensions, a bivariate normal, you can also do a histogram, but on this two-dimensional plane, right? Just cut this plane into many grids and count how many points fall into that grid. And you should see some 3D bars everywhere, right? The height of the bar going out of that. The height of the bar indicates how likely things will be there, right? It should be, let me not try to draw that 3D bars, but visualize that, right? And there's a 3D histogram that corresponds to a 3D bell. So this is normal. We typically call that this the bell-shaped curve, right? So this is basically 3D bell. Think about it. Yeah, a bell coming out of that, right? And the shape of this. So the lines I'm drawing is basically the contour of this bell, and the bell is squeezed in the sense that the more related Google and Apple are, the more squeezed the bell is. That means when Google has a high price, then Apple tends to have a very deterministic high price, right? And if it's round, if the contours are round, so this is a high correlation. The zero correlation are like this, right? So this rho is large. Correlation is rho, right? When rho is negative, you can have negative correlation. And you have the other side. Things like that, right? One goes up, the other goes down. That's negative correlation. That's multivariate normal. I think mostly we use two-dimensional bivariate. So just on top here, on top of the univariate normal, we need a mean and a variance. Here we have an extra parameter rho, captures the relationship of the two, right? So on top of, for each of the two prices, they have their own center, they have their own fluctuations, and there's another parameter controlling how they are related. Right? So, then next I will show you how to do all these things in R. So we would roughly go through these distributions, but not one by one, just quickly. Then I'll show you how to do some simple models, a linear model. I said the linear model is y is b0 plus b1x plus some epsilon. So think about what we need to do. There's only one x, there's only one y. We need to come up with some x right? We need some points for x. Then b0 and b1 are the parameter we need to specify. These are the truths in this population, right? We need to specify some relationship. Then we can go. This is going to be the fx. Right? Then we need to simulate some noise for each of the points. Simulate some noise. That end up we have some noisy data. Right? That's the simple one. And then we spend a lot of time on the 2D classification. So we have seen this last time. So that is two-dimensional. We have an x1 here, x2 here. So every data point comes with the x1 coordinate and x2 coordinate, and it has a color. Let me not use color. Let's just use a circle and a cross. Right? So this is for +1. This is for 0. Right? So everybody, that's the y. Right? Everybody has 2x and 1y. Y is the color. X is the position of the point. Right? And then let's not use x. Too confusing. It's also confusing here. Okay. How do we generate some points there? Right? And these are the tasks we have seen, I think, last time. But today we're going to spend a lot of time on these tasks. So we are given a data set. We know their x and their color indicating their y. So we want to figure out basically what's the relationship between the y, which is the color, and the position, which is the x, right? And when we do prediction, the question is really, give me a new point with its x, so I know the position. Can we predict the color of that guy? Right? That's the y of that. Right? So position is the x, color is the y. Okay? So we want to build a relationship between color and position, and eventually we can predict. Yeah. But before that, we need to generate a data set by simulating. Okay? Before we get in, let me quickly give you a preview of the R functions. So all these probability distributions are pretty standard, and so they have a big family of distributions basically in the same shape, doing the same set of things. Let me just show you these. So let's take example of a normal. Normal distribution. In R, the shorthand is norm. So there's a family of 4 distributions. For any distribution, you will find the same family. There's a R family. For the normal case, it's called R norm. R norm is a function. Do I need to? Function takes some input, right? Is for generating data point. Simulating points follows a normal distribution. So you need to tell R how many points you want, the number of points, what's the mean, what's the standard deviation, right? When you specify a normal, there's a mean, there's a SDE somewhere, right? And how many points you want. And then R will just generate a bunch of points for you. So this is the R function. R stands for, I don't know, but R means generating the data points. Right? And there's and later you will see if you replace this norm with like Poisson, is POIS, just replace the norm with some other. There's a binomial. What? Huh? Binomial. Yeah, there's a list of distributions. Just Google a little bit if you need a crazy one. That's R function, and there's a D function, D norm. D norm calculates this guy. So give me some x here. I will tell you how high is the corresponding bell curve for this. So this is the f, the PDF, f of x. So that's the height. So you need to tell d norm what's the x you were talking about, what's the mean, what's the standard deviation. It will calculate the height, right? This is especially when you want to plot the bell curve, and you say these are a bunch of x. For each of the x, tell me the corresponding height, and connect them. I'll get the bell curve. That is a. Are we okay? Stop me if it's too quick. There's a p norm. P norm does the probability calculating. So you tell me x, I'll tell you what's the area here. That's basically probability of that's a probability. Yeah? I'll tell you the probability. So you need to tell me x, mean, standard deviation. Yeah? I'm not giving you the height, but the area all the way to the left. What else? There's a Q norm. That's it, only 4. There's a Q norm. It's the inverse of P norm. P norm is saying, you tell me the cutoff, I'll calculate the area. Q norm says, you tell me the area, I'll find the cutoff for you. Right? That's the inverse of that. Say, suppose I want this to be Q, then the question is, what is this cutoff? Right? So you say, I'll give you a Q, mean, standard deviation. You calculate this x for me. That's the 4 probability functions. For simulation, we'll do R norm everywhere, but to verify, so very often you have generated 100 data points of normal. You want to make sure, is it really normal? So you plot a histogram and compare that with the theoretical bell curve. Right? That's later what I will do. Okay. Are we good? And in the future, we mostly do normal distribution and uniform. So we don't use all the crazy distribution. It's just good to know. There's no extra effort for these. So I have uploaded a document, simulation in R. I'm trying to lay down all the important things you will need. I have uploaded that to IBLE, I think. Yeah, I forgot this important thing, the groups. So let me pause for 1 minute. Right? So the grouping, I think I have some trouble here because we have 47 students. Let me check. So 47. So we have 47 students here, and 45 of you have formed groups, and the one is here, one is unassigned. So I can have a group of 2, but I'm calling for volunteers. Anybody want to move to the smaller team? The thing is, the evaluation of the project and the assignments will be based on how many people in this group. If this is a 2-person doing a project and 5-person doing a project, I'm having different expectations. Right? So let me know if you want to move to a smaller team, or if you don't mind, just help me solve that problem. Otherwise, I'll have 2-person in this team. Right? And just let me know by this weekend. If there's no volunteer, I need to either squeeze them into some group with 6. Then that group, the original 5 members will be worse off. All right. Oh, not this one. Okay. What I'm trying to say. You can find the document, right? It's under the lesson plan. So first of all, this document is generated by R. It's nice in the sense you can write whatever text in there. You can write code. The code things in the gray box are the original R code, and you can also embed the R output in the same document. So it has everything. Even later you will see plots all in one document. So this is a great tool. In the future, your homework and your assignment test will hopefully all in this format. And that's one part of today's homework. Go back and learn how to do this. I have put a link there, some online tutorials. And I also uploaded the source code of this thing. You can use as a template. You just need to modify things, not very difficult. This is a half an hour of work, very simple thing. But it's just a great tool for documenting what you are doing. You have the explanations, you have the code, and you have the output, all in one place. And when you submit your results to me, I don't need to run everything. I can just go through and see if it makes sense. Right? Otherwise, if you just give me the raw R code in the final exam, I need to run everybody's code so that I can see the output. And that would for sure crash many times. And, yeah. All right. I'm not going to talk too much about how to do that. That's pretty easy. If you understand R, that's pretty easy. So simulation. Now we talk about random sampling. This is more important than all the other distribution. There's no distribution. Just equally likely draw something from a pool of balls. So a quick example is I have letters, which is a vector, built-in vector. It's just 26 English letters. That's a vector of 26 items. And let's randomly draw 5 letters from this box. Right? So this function we use is sample. Sample, tell me where you want to sample. That's the letters. We want to sample from the vector of letters. I want to 5. Let's sample 5 of them. The output is 5 letters without repetition. So this is the default sample is take 5 elements out of this 26 without putting things back. So you cannot have 2 letters showing up at the same time. Right? So later when we split the data points, we'll basically use that. We have a data point with 100 points. Let's sample 50. So we had 50 here, 50 there. Right? So that's what we would do. And sample, as in all the simulation stuff, is random. So if you run the same thing again, you get a different set of 5 letters. Right? It's trivial. And this is default sample without replacement. And you can also do sample with replacement. For example, you can have a box called outcomes. So inside there's only 2 outcomes, head and tail. There are only 2 possibilities. You say, I want to basically flip the coin 6 times. Right? So I sample from this outcomes, and there are 2 in there, but I want to sample 6 times. The difference is this is with replacement. Right? I sample the head out, then put it back and do it again. Right? So this is with replacement. So essentially I'm flipping the coin 6 times and keeping track of the result. I'm simulating a coin flip. Right? This is a with replacement. We would do with replacement in Bootstrap. That's session 7 or 8. That's a strange way of generating data points with replacement. So you're sampling a data set, but every time you put it back and sample again. So it's likely in your new data set you have several identical points out there. But there's a smart idea behind. So we'll do that later. And without specifying anything, it will be a sample equally likely. So if you have 26 outcome or 2 outcomes, these things will come out equally likely. But if you don't like that, you can specify the probability. The probability should be of the length of the outcomes. Right? You have 2 outcomes, you should have 2 probabilities. So you can sample with and you can simulate an unfair coin in that sense. Right? These probabilities correspond to these two outcomes. Right? It's hard to see from here, only with 6 slips, but you get the point. So that's sample. Uniform. I said R is for simulating data points, and UNIF is for uniform distribution. So if I want to have 10 points uniformly distributed from 2 to 4, so that's the parameter for uniform distribution. I'll get these 10 numbers. They're all continuous numbers, and from 2 to 4 equally likely, and yeah, that's uniform. That's how we do for X. So give us some numbers. Don't care about the distribution. Equally likely. Poisson, we don't really use that very often, but R Poisson is for generating Poisson distribution, 200 points. For Poisson distribution, there's only one parameter, lambda. That's the average. The average number of earthquakes every 100 years, 6, right? Something like that. So you can simulate. These are the outcome of the Poisson variables. They are integers. They are counts. And here I'm just showing, these are not necessary for simulation, just to show if we have 200 points and R claims these 200 points are drawn from this Poisson distribution, can we trust this R? So we can do some quick statistics. On average, what's the mean of these 200 numbers? It should be, theoretically it should be 6, and we just do a double check. And what's the standard deviation? Who knows the standard deviation of Poisson? If there's a Poisson with lambda being 6, what is the standard deviation? What's the variance of a Poisson? Lambda. Variance is lambda. Standard deviation square root of lambda. Roughly. Maybe not roughly, but yeah, there's only 200 points. Yeah. And also you can check the distributions and the plots. So table is a handy function for, where's my point? Table is a handy function for checking distributions, right? We have 200 numbers. We want to know the frequency of each number showing up. So table does that immediately for us. It turns out of these 200 numbers, we only have 1, 2, 3, all the way to 13. Theoretically, it can go as high as infinity, but among these 200, this is what we have. Theoretically, we should have a 0, but it doesn't happen in this sample. And the second row is the frequency. That's the count, how many of each numbers show up. Right? If you don't like reading the numbers, you can just plot the table. Do I need to explain the plot part? You know how to do the R plot? Yeah. Anyway, for plot, here is just a bar plot because there's only one set of numbers. So I'm calculating the tables, but I don't want to just plot the count. I want to plot the frequency. So I use the table, the count divided by 200. That's the total number. That gives me the frequency. Then that's plotted as the bar chart, right? From 1 to 13. The first line of the code does the bar chart. If there's only one column of data, it does the bar chart, and the height is the. Oh no. There's 2 columns actually. Table itself has 2 columns. Sorry about that. Table has this 2 set of numbers. So it just does the bar chart. Second line, the bar chart shows the frequency in the sample of 200 data points. And second line, I want to compare that with the theoretical probability. Right? Theoretically, the probability, how do we calculate the theoretical probability? Remember that? We just say there's a D norm and D Poisson. That's the height of this curve. So I can easily plot that for number from, I did that from 0 to 15 because I didn't know it's in the range of 1 to 13. Right? But anyway, it doesn't show up. From 0 to 15, I'm calculating each of the points and draw a blue line like that. Okay? The second line of code, draw this blue line. And the third line of code, add the point marker, these small blue circles on top of each line, just to highlight these are the theoretical probabilities. On top of the line, I also want to have some markers out there. Right? I just, being able to visualize things would help a lot. If you just see the numbers, it's not so clear, right? Compare that, it's not so perfect, but out of 200 points, that's all right. And binomial, I'm not going to talk about. There's something similar. You can do the same thing in the comparison. Normal is more important, so let's do normal. So I want 1,000. Normal is continuous. We need more data points in that sense. So I'm simulating R norm. I'm simulating 1,000 numbers with mean 0, standard deviation being 1. So these are the so-called white noise going up and down. And I'm just plotting this series of x from number 1 to number 1,000. So the horizontal axis is just the index, and the vertical is the value. They just go up and down with no pattern at all, purely random, very noisy kind of thing. Right? That's this. But we can do the same. We can check the sample statistics. We know the theoretical mean should be 0, so we check this 1,000 number. All right, close to 0. Theoretical standard deviation should be 1. That's all right. And we can do the histogram. Histogram of this 1,000 number give us this histogram plot. And again, I want to overlay the true bell curve on top of this histogram. There's another handy function in R, so-called curve. Curve just plots a curve, and inside it can be a big function. Okay? We just said d norm is the bell curve, but for any given x, it plots the height. Right? And outside I have a curve function that automatically just do that for me. Just enumerate all the x and calculate the height and connect them in a smooth way. That's 1,000 points, close to theoretical value. Okay, that's normal. When we do normal, we need to specify the mean and the standard deviation. Right? Where's the center and how variable it is. Next, we need to do multivariate normal. We need to specify the mean, the fluctuations, and also the correlation. Right? Yeah, we just said. And multivariate normal is not a built-in distribution in R, so we need an extra package. This package is here, MVT norm, stands for multivariate normal. But the implementation is pretty much the same. But think about what we need. Where do I write? Okay. So when we do multivariate normal, we need the mean, mu, being two numbers, mu1 and mu2. Right? We have Google and Apple, we have two means. And we need, the other thing is the so-called covariance matrix. That is a matrix with how many numbers? 4 numbers. The first one is how much Google fluctuates. Second one, how much Apple fluctuates. And the off-diagonal guys are the correlation and their own. So there are only 3 numbers actually. Oops. Sigma 1, sigma 2, and the rho. Right? Rho is placed on the off-diagonal. That captures the relationship of the two. So we need these numbers to be put in the simulation of the multivariate. And where did I do that? So I did that here. So I want 2,000 multivariate normal random variables. And keep in mind, every data point here is a pair of two numbers, right? Google and Apple. Each row is one data point. And their mean is a vector of two. There are two numbers. And their covariance matrix is also called sigma, but big sigma, is a matrix with four numbers in it, with two rows, two columns. Right? That's the R way of writing a matrix. Write all the numbers and write the shape of this matrix, how many rows and how many columns. So that's 9, 3, 3, 4. 9, 3, 3, 4. Yeah, something like that. Yeah. And again, sanity checks. After having this 2,000 pair of numbers, which we need to check the average. But if we do mean, it just calculate the mean of all the points here. So we need a different one. This is the column means. So we calculate the mean of a matrix column by column. Right? Because we know the first column is for Google, the second column is for Apple. Right? That's what we want. Column means. This is also an important thing when you use that again and again. So that goes, theoretical value should be 1 and 2. And this is here. And also covariance, that give us the covariance matrix of this data sample. And we know the true, cannot point it over here. True matrix is here. Right? That's good enough. And plot. This is 2,000 data points, just like we have talked about. On one axis is x1, on the other axis is x2. Right? If we plot a scatter plot, that shows like that. Right? If you think about a histogram, outside 3D histogram, that shows how the two are related. Look at here, they are pretty highly related. So you have a narrow band towards the diagonal direction. If you don't like scatter plots, there's a 3D version. So finally, that's the 3D histogram. You can do that. Not very informative. And contour is better. So that's a slice of this 3D bell into many layers, right? So it's a slice. That's a contour. Not perfect, but yeah, that's from the data. So that's about individual things, right? How do we simulate things? Next, let's do the model. We have the individual components ready, and we can do the model. So we start from a linear model, as mentioned. The linear model is specified like that. Right? We want to make up a super simple population like this, the simplest possible. Two parameters, beta 0, beta 1, one variable input, x, and one noise, epsilon. And the population parameter, these are the true parameters in the population, and these are the things we want to learn. Right? So we manually set some numbers there. They don't matter too much. But yeah, you can like sigma here is the noise, the magnitude of the noise. Right? You can set yourself a huge noise or small noise. You can make your problem trivial and super hard. So this is a trial and error process. You need to adjust a little bit. Next, we need to do x. We need 100 data points. So how do we have 100 data points? First, we need 100x. We have no idea. We just do some arbitrary uniform from 0 to 100. Doesn't matter. Some x. 100 of them. Then we need 100 of noise corresponding to this x. So this is epsilon. Noise is normal with the mean, 0 with the sigma we specified here. That's the individual components we have talked about, uniform, normal. Next, we need to glue them together into our model. That is y. Y is determined by all these guys. Beta 0, beta 1, x, epsilon. Epsilon is determined by the sigma. Right? So everything is connected. And here the x is 100x I have simulated. Epsilon is 100. Epsilon I have simulated. So I just put them together and do a plot. And that's it. This is 100 points, x and y. And we know the beta 0, beta 1, right? So we can plot the theoretical line. So that's a true F out there. We call simulation, right? And the next step is let's hide this blue line. Let's run some algorithm trying to figure out this line and compare the two. And that's not the point for today. Just to quickly show you, if you really want to figure out this line, there's just one line of code, linear regression. Next week we'll talk about how to do linear regression. But you basically just need to tell what's your output, what is the y, what is the x. That's it. You will get some output, some intercept, some slope. Yeah, we'll do that next week. So that's the simplest possible model, right? And you can compare the estimated line with the true line. Now the important thing, right? The classification. That's closely related to today's data. So I have described this thing to some extent. So we are moving to this guy, right? So we have two x, x1 and x2, and each point has a color. So in practice, how do we do that? Let me go back. Let me draw something. Let me add an empty. So how do we generate points here? x1, x2. We need some points. Just like in the easier example, we first need to have some x, right? And now we have 2x. So you can generate x independently. But the standard way of doing this is to have, eventually you are going to have one group of red points and one group of green points, right? That's eventually. So we may think about this way. Let's separate the 2 points, treat them as two families. So we first generate a bunch of red points. We say the red points, the position of the red points, right? The position is determined by x1 and x2. We are only generating x, and the y is fixed. Y is 1. So that's the red guy. Okay? So how do we get that? We say, oh, all the red guys are actually coming from these bivariate normal distribution. That is ugly, but think about a bell, right? So that tells you the center of the cluster of the data points and how wide it can spread out. So that's we need to specify a bivariate normal distribution out there. Then we get some points. Hey, there's some guys, some points, some points. Right? So I get some points, a bunch of red points. Next, let me change your color. Let's do the green one. These are the y0. We still need to simulate their position. Right? We specify another center. It doesn't have to be circle, just to make things easier. So this is the green one. So I'm having some green points. There might be some crazy guys. Go there. Right? So that's a bunch of green points. Then we imagine we don't really see the circles. We only have the red points and the green points, and we are done. Right? That's two family of points with their corresponding x1 and x2, and with their corresponding color. Right? And we are done. That's how do we do this thing in practice. That's not necessary. You can just do uniform x1, uniform x2, you can do that. But I want to introduce this because the ugly data we are going to work with is going to be kind of generated this way. This is the simplest possible case. You only have two groups mixing up together along the boundary. And the crazy data we're going to dealing with is 20 such things all grouped together. But no, not 20 such clusters, but 10 of them are red guys. The other 10 are green guys, but they're just messed up around. Right? Earlier you have seen the crazy picture. This is the resulted. This is a mixture of 20 ugly things. We'll get back to that later. But with 2, that's easy. That's easy to imagine, right? So let's do that. So how do we? Where do we start? We need the x, right? We say we define. Here I use red and blue, right? I define the center because this is a multivariate normal. I need to define the center. I need to come up with the covariance matrix. So I have the center for the red family, center for the blue family. That's their means, basically, the mean of their position. Then I have a covariance matrix. I'm a bit lazy here. I just use one covariance matrix for the 2 families. They share the same shape. Right? That doesn't matter. So let's have 100 data points from the red family. So this is a multivariate normal. I want the 100 data points. Their center is the red center we define here. The covariance is just this guy, just circles. So we have 100 points. And we do the same for the blue ones. So the only difference is here. I'm replacing the center going from red to blue. Then I can plot this, guys. Just don't worry about the plot, but that's a picture. Right? That's a bunch of 100 blue points and 100 red points. I have highlighted the centers. That's the true center, just to for the sake of illustration. Right? In practice, you don't see that. You just see these 2 groups of points. And again, the task is we want to learn the relationship between the colors and the positions, right? And so as to predict the colors based on the positions. Right? And yeah. And at the end of the day, what we hope we can say is, by looking at this training sample of 200 points, we can comfortably draw a line somewhere that we can say everything on top left corner are going to be red. On the other side are going to be green. Right? So that's the ultimate goal. By looking at the training data, we ultimately we want a boundary. And you give me any point in this space, I just compare that point and the boundary is on the top left side. I would label you as red. That's my prediction. Everything on the other side will be green. Right? That's just a preview of the results. Okay? Conceptually? Okay? Mm-hmm. Yeah. Yeah, exactly. The difficulty is when they overlap. When they are far away from each other, that's a nice situation. It's not easy because you can cut this way, you can cut this way. They're all separated. You don't really know which one is correct. But when they are overlapped, that's the beauty. And now it's only 2. The 2 overlaps are okay. You can draw one straight line to cut them separate. If there are 5, you need to do all these things, right? Yeah, they can overlap a lot. Like in this part, there are a lot of it's hard to say what do we mean by overlap. They just all mix together, right? Without knowing the circles, you don't really have a definition of overlap. They just mix. And yeah. So we're done with simulating a nice 2-dimensional classification data sample, and we can apply. Later we will do the k-nearest neighbor, and we apply that to something like this. Right? That's about simulating some homework, not homework, exercise for yourself. Okay? Last piece of handy function is the so-called set seed. Because we are simulating, everything comes out as random. And the good part is it's random, and the bad part is every time you run your code, you get a completely different not completely, but slightly different positions of these points. And that's going to be a disaster in your exam if you're interpreting other results, but your number changed after rerun everything. And that's going to be an issue. So we have a function called setSeed. So just put arbitrary integer number in there. So it makes sure whenever you set seed, it makes sure the following sequence of the random numbers, they're still random, but they're fixed. So pseudo-random. This is so-called pseudo-random. So statistically, they are still random numbers. But in fact, like we just run the same thing again. Although we are generating 5 random numbers, we get exactly the same thing. Right? So this is a quick thing. Whenever you're simulating something, set the seed at the very beginning, so that every time you run, you will see the same set of random results. Yeah. No, there's no difference. It's basically at the back end, there's a big pool of numbers you just cycle. Seed just determines when do you start to draw numbers. So just think about there's a huge wheels with a bunch of numbers. You say seed determines, let's start from here. Let's draw a number like this. You change a different seed, you draw from there. Yeah, but yeah, that's roughly that. Okay. That's simulation. Everything is there. Are we all good? I hope. All right, K-nearest neighbor. As you said, this is the simplest possible tool. It just takes one sentence to explain. Just one sentence. Not this sentence. So come back to this sentence later. This sentence. So it basically says you have a data set and you want to predict based on that data set. You just find several neighbors around that point you want to predict and use their value, take an average, that's your prediction. Okay? What do we mean by that? Just think about earlier the color example. We have x1, x2. We have several data samples. Right? So that's a data set we have. Now we need to use this data set to predict a new one. Say this guy. I want to know this guy at this position, what's the color of this guy? I want to use k-nearest neighbor. Let's say k is 3. Let's say let's look at this red guy and find the 3 nearest points in my data set. What's the 3? We say roughly these 3 guys. Right? Out of these 3 guys, I have 1 cross 2 circles. So majority wins. So I'll predict my point as circles. That's it. Done. If it's a regression, we just average the 3 values. This is a classification. We just take a majority vote. There are 2 circles, 1 cross. We just do that. And if you need a probability, later we'll need a probability. So majority vote is really, you have to assign a color to this point. I will put a circle there. But sometimes we want the probability. We'll say something more. So sometimes we want the probability of being circle is the proportion of circle. Okay? There were 3 points as the neighbors. 2 were circles, so the proportion was 67%. So I'm predicting this guy to be 2/3. Right? The probability of that.
What if the sequence, like the
yeah, randomly choose one. Yeah, there are a lot of little technical details. What if you choose 2 neighbors and one is circle, one is cross? Yeah. In general, we don't choose 2 neighbors. Because this is a majority vote, we use the odd number of k by choice. Odd number of k, so we always have a majority. But some others may say, what if you have a bunch of points, they're all equally far away from this? Yeah, choose any. Just randomize. Whenever there's a tie, randomize a little bit. It doesn't hurt. So there's some little details, but Well, that's the algorithm. That's it. Are we okay? So for the regression problem, every point comes with a y, so you just average their y. For classification, you take a majority vote, you get the labels, or you calculate the probability. That's the proportion. You want the proportion of zeros or ones, up to you. You get the proportion. That's the algorithm, and this algorithm is the so-called non-parametric. So we introduced non-parametric earlier. It's different from the linear thing we said. At the end of the day, we get an intercept, we get a slope, and whenever there's a new point, we plug in this formula, we calculate. That's a parametric. This guy has nothing. What do we learn from? What's our model here? After we didn't train at all, we just said we're done already, right? So we didn't even train. But how do we describe our model? How do we say we're done, but we can use this thing to predict any new points, right? But what is in our model? Or think about if you want to encapsulate this thing as a function. What are the information you need to carry? What are the things you need to know so that you can predict? What are the information? Yeah, you need the whole data set. Because you don't know where the new point is coming from. You don't know which ones are the neighbors. So you have to memorize the whole data set, the whole training sample. So basically, your model eventually is the training data set and K. You just need to tell me these two things. I can run this, right? Just K is the extra number, but I have to carry the whole data set. Otherwise, I cannot do this, right? So this is non-parametric. You have to carry the whole thing. It's a problematic. Well, that's not the main thing, problematic. This thing is not really useful. Let's think about it. But I chose to cover this because of K. K is the only input we need to impose on this tool, but K plays a critical role. Think about when K is. Let's think about the two extremes. K goes to infinity or K goes to 1. K goes to infinity. No, it doesn't work infinity. K goes to n. You cannot have infinity. N is your size of the data, right? What if I have 100 points and I'm taking 100 neighbors? What I'm doing? I'm taking all the data sets and take an average of everybody and using that as my prediction. So what's going to happen? Yeah, whatever the input or the new point is, I'm going to provide the same prediction. That's the average of this 100 points, right? So that's an extremely inflexible thing because it always tells you the same number, right? It still captures some information from this data set, but that's just the average. How about the other issue? K equal to 1. K equal to 1, I'm just searching for the nearest neighbor, the single nearest neighbor. Right? I use that if that guy is circle, I just take circle. Right? So think about, I move a little bit the point, and I might be assigned to a different neighbor because a different guy becomes my nearest neighbor. Right? So the color of any point can change very frequently if you move around. Right? There are a lot of changes. It can be very flexible. So later I have more solid illustration. But just intuitively, when you take less neighbors, there's more fluctuations. Right? When you take more neighbors, it's more stable. It doesn't change very frequently. But that's a nice parameter for us to play with so that we can illustrate how do we do overfitting and how do we do underfitting. But before we illustrate that, let me highlight several things. Right? In the future, whenever you think about using k-nearest neighbor, think again. First of all, there's a, do any of you see the issues? You can see the slides, right? Okay. No. Anyway, nearest is not well defined. That's number one. Right? Think about this is x1, x2. We don't know their physical meaning. We just treat them as numbers. Right? What if x1? Think about last time. x1 is the income of someone. x2 is the seniority. So income is some dollars. Right? If this is some dollar thing, and this is some year, how many years of working experience? How do you make a judgment about distance, this distance versus this distance? Right? This distance is $1,000. This distance is 2 years. How do you say which one is closer? How do you? This is not obvious. Right? But this one has a solution. Later we will have other methods using distance as an input. So whenever you have this such situation, people do like a normalize. So everything is normalized to the relative scale. So everybody has some income, let's minus the average, divide by the standard deviation. So everybody's income becomes a relative number. Right? That's you are at 90 percentile. I'm at 20 percentile. Right? That's a relative scale to the point. And your seniority is also scaled 90 percentile, 20 percentile. That's more reasonable than this at least. Right? It's not a perfect fix, but it's more, at least you take out the unit issues. Right? You're not talking about trading dollar with years. And the more controversial part is when your X are categorical. Think about this is about your gender, this is about your other things. Now you need to say the distance between male and female can be equivalently treated like the distance in the number of years of seniority. There's all these ethical issues you deal with. So when it's categorical, the distance is a bit even harder, right? We said when you have two categories, that's still fine. They're different, so there's some distance of 1. If you have 7 categories of colors, how do you measure I'm red, you are green? What's the distance of how do you measure that? Right? And so whenever you have categorical variables, this distance thing is very hard to work. Yeah? And in almost all the applied problems, I don't see any data set without categorical variables. You always have those things. Right? But that's number one. Number two is today's homework. That's the dimensionality. This thing works okay when you have 2, 3 dimensions, 2, 3x. When you have 20x, it's just very bad. That's today's homework. You can experience that by doing your own experiments. Simulate some data. Good. Yeah, exactly. That's exactly the solution. The solution is if you can, right? If you can, we say this thing doesn't work with 20 dimensions of x. So we have the PCA that shrinks the dimensions of x. Right? If we can shrink to 3, then we can apply this. That's exactly the point. If you want to use this thing, think about dimensionality reduction kind of tools. Right? Good. These are okay, so you have a fix. If you worry about dimensionality, you have a fix. Worry about the scaling, the distance issue, you have a fix. The thing you don't have a fix, you don't have a cheap fix, is variable selection. So in all the other tools we are going to learn, there's an important component of selecting which x will be in our model, which will not be. There's a judgment part. X2 is important. x1 is irrelevant. I want to throw x1. I don't need that anymore. This doesn't have that part. If you have 20x, how do you decide whether to include or not include this 20x? You have to put everything there. So PCA solves part of the problem if you can shrink them. But naturally, the variable selection, that's basically the most important part of all the tool. It doesn't have that capability. And the fix, if you really want to fix, you can fix. You can run other tools with a variable selection capability. Select the variables and use those variables, then do the k-nearest neighbor. But if you are done with other tools, you don't really need to go back here. Right? Most of the time, you don't need to do that. So these are all important things. There are much better tools that can handle this. Yeah. So yeah, let's not worry about these things. Let me see. Yeah, I think in my whole career, I have seen the good application of k-nearest neighbor only once. Once, it's not easy. There's a good use. Those guys was trying to use the Wi-Fi access point to locate the customers in the shopping malls. Right? They have free Wi-Fi. The access point is everywhere, and customers carrying their phones with Wi-Fi turned on. So your phone is always searching for Wi-Fi to connect. You're sending all these signals. Right? So by measuring the strength of the signals, they roughly can get your distance to a particular access point. But that's super noisy because all these walls, all these interference, all these things, super noisy measurements. So the solution is to have many access points. So most of the malls install more than needed, just for the signal issues. So they want to accurately locate all the customers. Where are they moving? How often they go to toilet? All these things. So there was an application used k-nearest neighbor that's basically that. So they want to basically figure out all these access points can measure the signal strength to a particular phone. Right? So I have 10 access points on the roof. They can all measure the signal strength. So they're all translated into a noisy distance measure. There are 10 distance. So by triangularization, you want to find the location. But because of the noise, it doesn't work. So they say, let's do a non-parametric way. They just hired a lot of people, carry their phones, stand at a known position, collect this information about the signal strength. Right? You have a training data with the true Y is your location, and the X are the signal strength. They're super noisy, so they need many, many measurements. And you move 1 meter to the side, collect all this information, move another meter. And they build this relationship between the signal strength and your location in some sense. And that's like a 10-dimensional. You have 10 inputs at the same time. And yeah, that's something like that, I think. And then the nice part is really because all these 10 measures are homogeneous. It's not like dollar years. They're all some sort of the same thing, right? Some sort of thing. That's a nice kind of application. Yeah. All right, let's take a break. So we come to the coding part, right? Glued it somewhere. Make sure it doesn't move. tough job. Good, we solved the problem. Yeah, now we get to the coding part. Right? We talk about how the algorithm works. Let's get to the coding part. The first thing we need to note is how do we measure the training error and the test error. And we say we already have a data sample. This is, I'll change that again, orange and blue colors of points. Right? So this, together with k being 3, is going to be our model. And whenever there's a new point, we use this data sample, find the 3 neighbors, and figure out the color by majority vote. So how do we do that out of sample if we get a new test data? And that's this part. We're not really getting a test data. We are getting the whole population in this case because this is simulation. We say, since we have this model, we can predict any given point in this space. So let's just do that. Let's just enumerate any given point in this space. So we just create a big dense grid. So every this tiny point is one candidate of the points we want to predict. We just apply this algorithm throughout all these tiny points. For each of the points, eventually it will get a color. So we just color them according to the prediction. So there's a bunch of orange guys, a bunch of blue guys. Okay? Are we fine? So think about in this corner, they're all orange because think about, if you think about the 3 neighbors, all these guys will have this guy as the neighbor, this guy as the neighbor, and this guy as the neighbor. They all have these 3 neighbors. Out of the 3, 2 are orange. So they are all going to be orange. But gradually you go down to these guys. This point is no longer the neighbor. Instead, maybe this one. So think about for the blue points here, these will be the 3 neighbors. Okay? So they're now colored blue. Right? That's eventually what we just enumerate all the points in this space and color them. This is pretty quick process. And at the end, we actually highlight a boundary. Right? We just connect the boundary, connect the points that is on the boundary between orange and blue. So we just say these are actually our boundary. So in the future, whenever there's any point, we just use this boundary and make a judgment. Are the new points on one side or the other side of the boundary? And that's our way to determine the color. Right? So we say this is the training sample. This dense grid is the population. We can actually measure if we are doing simulation, we should know the theoretical true color of every point in there, so we can compare the errors. So this is going to be the first time we see the out of sample error, because we're talking about pretty much the whole population. Right? It's not exactly the whole population because still it's a grid. There's some discretization out there. Okay.
So actually, you have to calculate every small point in the graph.
For what?
To calculate the probability of the every point, right? And the complexity maybe if you have a very large points in the graph, you have the complexity is very large.
Yeah, we don't need to do that. Yeah, just out of sample error for the whole population is just a theoretical concept. There are infinite number of points in this population, so you cannot enumerate all of them. You can always have a dense enough grid that the whole point we do this is we want this boundary. If you think this boundary is accurate, not granular enough. If you don't like that, you can make a denser grid, right? So, but this is good enough, right? Of course, there's a trade-off. Like if it's slow in coloring one point, we may increase the size of the grid a little bit. Yeah, there's a trade-off. But this is a trivial example. You can easily do that with all these points. This is only several thousand points. That's pretty quick. Yeah. Okay. So that's a illustration of what we are going to do, but we are going to work with some more complicated data. Looks more like this by simulation. So earlier we said how we simulate two families with some overlapping circles, right? So this is an example. It's not exactly what we are going to work with. This is a simpler version, but this is an example of like many families all mixed up together. But yeah, but at the end of the day, there's some orange, some blue, and there's a theoretical boundary. So this is a theoretical boundary because we are simulating. We know there's a clear cut on this space that on the one side, the points are more likely to be orange. On the other side, the points are more likely to be blue. Because we are simulating, at any point, we know the probability it should be blue or should be orange. And this is a boundary for 50-50. Everything on one side has a higher probability to be orange, larger than 50%. On the other side is blue. Right? So just like when we talk about our simulation with two families, the theoretical boundary is a straight line. It's a straight line, but this is the small things involved, so you get a really curved boundary. So we want to make this problem more difficult. If the straight line is too simple, it's too quick, right? We make it more difficult. And the real data we are going to see is more complicated than this. But just a quick preview of the results we are going to do. So if we do a k-nearest neighbor on this data sample, again, we're doing the same thing, right? All these big circles are the data sample, about 200 data points. Then we apply everything on the whole dense grid, apply the k-nearest neighbor with k being 10. Using this sample, we can color them. Then we can find the boundary according to the colors. Okay? So that zigzag line is the actual boundary suggested by the k-nearest neighbor algorithm. Okay? So we can compare that with the true boundary we know because we're doing simulation. So we can see this is a pretty good algorithm, captures most of the shape. It's a little bit noisy, but yeah, it captures the main pattern out there. So this is when there is a k being 10. And we just said k captures the flexibility, but we didn't talk about how do we choose k yet. So this is going to be one way of choosing k. So we try one k there, and we will try to measure how good this thing performs out of sample. We need a test sample for that. But later we'll do that. But before that, let's try other k. Right? So earlier we said k equal to 10 is roughly the best situation we can achieve. But let's see the two extremes. When k is equal to 1, what's going to happen? So that's kind of a more noise, more zigzag. Then we have a lot of tiny islands in this sea, right? So because k is equal to 1, you have a one blue point out there. Every single blue point creates a small island. Everything close to that guy is going to be labeled blue, right? So because of this y, right? So that's clearly overfitting because you're picking all these tiny noises into your final boundary. Okay? Every blue point in there will create a small island out there. On the other side, that's k being 100. I think this is 200 data points. K being 100 is very inflexible. It's basically draw a roughly straight cut. Okay? So it's not flexible enough to capture this curvature, but it gets the main point correct. It's not perfect, but it gets the main point correct. So this is an underfitting when you have only partial kind of pattern. This is overfitting because you get all the noise into your final boundary, all these things. Right? So that's a quick way to visualize what do we mean by overfitting, because all these little points are kind of some tiny noise, right? So next is about choosing the optimal k. How do we do that? One way is to have a test sample. But here, since we have been doing the grid already, so we have the grid, we have the true boundary. So everything on one side of the true boundary is supposed to be orange. On the other side is supposed to be blue. So we know their true color. So we can actually compare what the true boundary determines and what the algorithm determines. So we can measure the error basically directly on the grid. Okay? So we can count the error rate. So that's the picture. This horizontal axis is a bit weird because last time when we plot the conceptual picture, we have overfitting on the right side, underfitting on the left side, right? So we want to do the same thing. So we plot it on the wrong side. So this is k equal to 1. This is 1 over k, right? The couple. This is k equal to 1. This is k equal to 100. Right? We say this side is flexible. This side is inflexible. Right? So this is basically 20, 10, 5, 2, 50. Right? Let's translate that to k. Just for the sake of consistency, we plot this way. So we have two lines. The blue one you can imagine that's the training errors, and the test error is the orange one. Last time we have seen the conceptual ones. They are smooth, they're nice, they're decreasing, but this is the reality. We said ideally this thing should go down, but it's still up and down, a lot of noise. Right? Just at the beginning I mentioned some of noise are coming from the training data, some of noise are coming from the test data. So all these noise add up together, making these lines just up and down, up and down. Right? So they're not perfectly kind of monotone. Let's see the training thing. Right? When nearest neighbor algorithm becomes more and more flexible, your training error goes down, 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 eventually to 0. So why, when k equal to 1, we are having 0 error? Good. So basically, we are memorizing we are carrying the whole training data anyway, and now we are using that whole training data to predict on the training data itself. Right? We're getting 0 errors. Let's think about what are we doing. There's some points. Right? Now, this is my model. I have a k being 1. So now you ask me to use this model to predict on the same set of data. Right? That's a training error. So the same set of data. How about this guy? We need to find one nearest neighbor. Who's the one nearest neighbor? Itself. Right? So we use itself true y as the prediction of it's y. So we are going to be perfect. Right? Then we do the next one using itself. So we're always using itself to predict itself. This is a good example of cheating. Right? So that's a good example of cheating. So we are going to be perfect because we memorize everybody, and we're going to be perfect. Right? But when k equal to 2, that may not be perfect. Right? We still need to find another neighbor and take an average, all these things, and that may not. Yeah. But k equal to 1 is an extreme case. What else? Oops. There's also a irreducible error. I put it here. This is also because we're doing simulation, so we know what we mean by irreducible error. It says even if we know the true boundary is this guy, even if we use the true boundary to classify all these points, there are still errors because there's some weirdos going to the other side. Right? So there's still going to be some errors. This irreducible. Irreducible error can be calculated theoretically. Later we will see, but there's a thing, right? Because we're doing simulation. Also because we're doing simulation, we see the test error goes very close to irreducible error. That's a good signal. That's quite close. Yeah. Anything else? So this is a quick illustration of what we have talked about last time. training error, what do we mean by cheating? At the test error, there's some U-shape underfitting, overfitting. Okay, next we will do coding. We will repeat the same thing in R, the linear problem and the coloring problem. The linear problem is simple. We just want to illustrate how do we do this thing in R. Oh, yeah. In the data we talk about. Here, I forgot to say. So how do we pick the K? So based on this thing, these are the good guys, right? 20 to 5, roughly in this range. If you want to be really crazy, you choose the minimum point, roughly 20. But keep in mind, all these things are fluctuating a lot. There's some noise. You can see, by looking at these lines, you can see the level of the noise can be this much, right? So it's not necessarily safe to say this point should be better than this point, because of the magnitude of this noise can be quite big, right? In that sense, we look at this thing, we may say roughly all these guys are similar. Due to this noise, it's very hard to differentiate them. If that's the case, we choose the less flexible one. If you don't have a good reason to believe there's some way to differentiate them, choose the less flexible one. Less flexible one is safer. It's a simpler problem. It's safer. It's less subject to overfitting. We'll come back to this somewhere later when we talk about how do we choose. In all the other tools, there's a parameter we need to choose this way. This is the fundamental picture we'll see again and again in all the algorithms. Good. Good. Let's keep that in mind, right?
Lot of different testers that to find optimal K. In that case, you only find one tester data to have the orange line.
Yeah. If you have access to more data, definitely you should use more data to smooth that. Right? This is not smooth partially because my test data is small. Right? Think about why this is not very smooth. One is maybe because the training data is small, so the algorithm I'm carrying is not very stable. Yeah.
Do I have to divide, if my test data is very large, do I have to divide my test data into different groups and then apply my assumptions into those groups many times, or do I have to use a large group to use it as the test data to test my assumptions?
Two answers, right? In general, you don't get very large test data. If you have a large test data, why not use that in training? In most of the situations, you never have that struggle. If you really have that struggle, it doesn't matter, right? If you throw all the test data as one big chunk or cut that into many chunks and throw it one by one, you eventually will aggregate all these error rates altogether, right? Doesn't matter how do you do that. But in reality, you don't have that. You have a finite sample. You need to cut your finite sample into training, validation, and test. You would never have that luxury to worry about that. Yeah. But but there are two questions, right? Earlier there was a question about would the optimal K depends on the size of the data. Right? Keep in mind how do we think about that. There should be a quick, intuitive way of thinking about that. But later we'll do an illustration. Yeah. And the next thing is when we are building our model, there was a little bit slack there. When we were building our model, we actually specify the K directly. So this is a given 10, K is equal to 10, we do this thing. Right? So actually we didn't use the training data to determine the K. And we have to determine the K, use another data set. Right? So when we do the training, we didn't do anything. Right? We just carry that data and apply that to do the prediction. In order to choose the K, we actually need another data set. And here we call that test data. We use that data set to do to measure the out-of-sample performance and to choose the K. Right? So, but if we are doing that here, this is no longer test data. This is the so-called validation data. Later we'll come back late. There are 3 rows in your data. The training for kind of calibrating the parameters in your model. Here there's no parameter anyway. Then there's a validation for making model selections. So you have a bunch of candidate models. You don't know which one is good, which one is bad. So you apply all these models on the training set and evaluate them on the validation data and choose the best one. So that's exactly the validation process. So validation data is used for model selection. Then there's another one is the test data. Test data theoretically should be somebody else test that for you. You will never see the Y's. You will never see the errors. Somebody else measure that. If you see the errors and go back and change your model, you are cheating. Like we cannot see the exam answers and go back to let's study again, right? That's cheating. So if we treat this as test data, we shouldn't go back and change our model anymore. If we look at this orange curve, we say let's go back and choose our K. That's a validation. That's based on this information, we are doing a model selection. Right? That's a self-exam. Like think about a self-test. You're testing yourself, say which way of learning is better. Oh, turns out this is good. Let's use that one to go to exam. Right? That's in general, in practice, when we have a data set, we will cut that into 3 chunks, the 3 rows. But there's some smarter ways of doing that to make a better utilization of the data. We'll come back to that later. But for now, you can think about there's always 3 types of rows in any data set. And very often, that's also a trade-off. How many data you keep for training, how many you keep for validation, how many you keep for test. You want your every step to be very certain, less noisy, but then you need more data to do that. So there's a competition for data in that sense. Okay. We'll talk about the roles of the data later. This is not very rigorous. We have a better way of seeing the flow of having a data set. How do we cut that and do that? Okay, coding? Not much time. So I'll do the linear one first, and the linear one is to show you how to use the k-nearest neighbor function. That's the main point. Solving that problem is pretty easy. And earlier in the afternoon class, there was a lot of doubts about why are you having such a long piece of code on so many things. If you just want to do k-nearest neighbor, I think in the whole piece of code, there's just 3 lines are relevant. But a lot of things I'm adding new visualizations, extra check, all these things, just to illustrate something in the middle. Right? It's not the standard workflow of the so tedious long thing. So we're in a regression case, we are simulating our own data. We specify the function like y is a function of x squared, and x cubed. So they're basically 3-dimensional x. They're all based on the same x. That's easier for us to plot. But theoretically, they're just 3 different x. You can think about them as x1, x2, x3. And then there's a noise guy. So the simulation thing is pretty much the same. Just let's manually specify all these critical parameters we want to learn. Then I set a seed and simulate the x. I have 100 data points. Is that big enough? Everybody can see? I can enlarge it. Let me enlarge. Better? Yeah. I'm simulating 100 data points for x. How do I move up? What? No. 100 points from 0 to 5. Right? Then fx is the specified structure of the y, beta 0, beta 1, all these. Then epsilon is the noise. Just like before, we have a 0 mean and some magnitude of variability. Y is fx plus epsilon. Okay? That's the standard thing we have gone through. Visualization. Let's plot that. Do I need to explain the ggplot thing? ggplot is the package that makes R very popular. Nice way of plotting things. You can see have you done this in the boot camp? No? Yes or no? The red and the green in the population. Okay. So learn from each other. This is important. But anyway, ggplot has a layer concept. There are many layers of things you can plot one by one, and you could add them together. So the first layer is it's not working. First layer is the canvas. I have nothing. Then there's a layer of points by specifying x and y. That's my training data, right? X and y. I have this bunch of black points. I'm making it a little bit bigger. Then there's a layer of line. And geom means geometry, so there are different geometry. And the mapping is x and fx. So I'm plotting the true fx, this is the black line. Right? Just like the picture we have seen in the last session. So this is simulated. We have a weird curved underlying function. We add some noise. We get all these things. This is just to choose a black and white background. All these are by layering. Just make the points a bit bigger. So you can change that to 20. So if you want to know, just change that and run it. Test data follows the same argument because I know the population, so I can simulate another 50 data points exactly as I have done for training. Let me plot the test data. This is just an independent set of data with 50 points from the same curve. Okay, so we'll go by x, y, and x dot test and y dot test. Right? That's just 4 data sets. So the k-nearest neighbor, the one bad thing about R is every function you want to do, there many packages can do that. K-nearest neighbor, at least there was 3 or 4 packages, so I just picked one. All of them are pretty outdated, old-style, not modern. But anyway, so you can load this function KNN. Inside, there's a function called KNN.reg, reg for regression. And I think that's one part of things I think is important is you're not here to learn how to use KNN.reg. Learn how to dig this thing out from the documentation. Right? This package would be outdated in 2 years. Nobody would use that. There will be new packages and new things. Right? Learn how do you learn to use a new package. Read the documentation and figure out what they're trying to do. Right? And you have the proper foundations. It's pretty easy to see. So I find this function from the package documentation. There's a KNN, there's a KNN.reg. This is for regression. The other one is for classification. Right? K-nearest neighbor regression. Look at the input. This is a pretty ugly function, actually. How to say? In the future, there are a series of tools we are going to learn. They all share the same shape of the functions in the sense that if you don't want to use linear regression, you can just change the first 2 letters and replace that with a random forest. It just naturally carries. It uses all the same format and same shape of input. But this is a bit outdated. So it takes many inputs. Not surprisingly, you need to specify k. And k equal to 3 here means if you don't say anything, they will assume k to be 3, right? And then there's a train, there's a y. That's the x in the training data. That's the y in the training data. This is a bad way of doing that, but in the modern things, next week we will see the modern way of doing that. The critical one is really this test guy. The other things are natural, right? You need to specify what's the x, what's the y, what's the k, right? That's necessary. And there's an algorithm for searching for the nearest neighbor. In a big high-dimensional space, finding several neighbors is not trivial, because you have to measure the distance to all the other points so that you can say these 3 are the nearest. It's not a trivial computational task. So there are some heuristics of that, but let's not worry about that. The troublesome one is this guy. So this is a bad old-style function that combines 2 things in the same function. So we're doing 2 different things. The first part is training the model. The second part is predicting on a new data set. It's supposed to be 2 separate tasks. It should be done in 2 functions. But somehow they just combine this all together. At the time of building this function, you need to specify a new data set so that they would do the prediction on that. Right? And the trouble is, if you don't specify that, it will do some funky things. Cross-validation, leave 1 out. We'll talk about that week 7. We'll come back to this point again. But since we're not there yet, so we have to put something there, right? Not leave that empty. But later you will see, if we want a training error, so we would need to predict on the training set itself, so we put the train data here. Or if we have a test data, we just put the test data there. Yeah? But that's the documentation. And the output, there's also some description of the output. I'll just show you the output is pretty intuitive. And the other part of this old style is the input is supposed to be in a matrix shape, just converting everything into matrix. But in that sense, we only have 1 x, so actually there's just a matrix of 1 column. Okay? And train x has 100 data points, that's here. Test x has 50, right? 1 column. All right, we're ready to do the k-nearest neighbor. Let me run that first. So we take the training x generated here as the training x also as a data set for prediction. So we're doing the training error here for the sake of demonstration. Then we have y, being y. K is 15. So I've done the enumeration. I found 15 is the best. So let's start with the best. So I've done that. The output, I have saved that into this object model 15.train because I'm predicting on the training data. Right? I label that as .train. It's here, this guy. It's a list with many other many information. First, almost all the R package would keep track of how you call this function. That's just what are the commands invoked this whole thing. Then k is 15. That's our input. N is the size of the data. It's figured out from the data. And the only thing matter to us is the prediction. This is a pred. So this is a prediction because we provide the train data to predict. So there's 100x there. So there's 100 prediction out there. So that's 100 y here. Okay? So that's the only thing we want. And str is a good function. If you have something you don't know what's in there, just type str. I don't know what's the meaning, but it just shows you what's in there. Let's do the plot. What do we do here? So we just say ggplot is a great thing. This is the earlier plot I have saved, plot.train. I just need to add another layer that's a line with x being x, y being the prediction by the k-nearest neighbor model. and that's the blue. I set color to be blue. So that's the blue line you see. That's the top layer, not big enough. What do we see? The blue line captures the pattern pretty well, right? It matches the truth almost perfectly. How did we do that? We basically pick, for each of the points in the training data, we pick the 15 neighbors. Again, we are predicting on our own. We're predicting on our own the same training data, right? For each of these black dots, we are picking ourselves and 14 other neighbors and calculate the average. We save the number. Then we have 100 of them, so we have 100, that's y. Then we connect this 100y using lines. That's the blue line. Okay? That matches. Well, that's not what we do in practice, because we don't do this in sample. But at least we can measure the training error. That's, for illustration, we want to measure the training error. So this is a regression problem. Training error is mean squared error. We talked about that last time, right? Mean of the squared error. Error is 2y minus the prediction. Right? Mean squared error. What is the mean squared error? Where's my number? Where is the error? 3.83 something. Yeah? The error itself doesn't mean anything. We need to compare that with others. So that's the illustration for training on training. Now we really use the test data. So we change that to test. We use the 100 data points as the model and predict the 50 out of sample. All the other things remain the same, and not. That's still pretty okay. Okay. That's still pretty okay. That's for each of these 50 data points. So these 50 data points are plotted against their true y. Right? The height is their true y. Their x is actually somewhere here. There are 50 points on this x. So what I'm doing is, for any of these x, I'm using the previous 100 data points, find the nearest neighbor on this axis. Right? The neighbor is always based on x, the distance in the space of x. There's only one x. So for this guy, the x is here. I'm having several neighbors from the training set, 15 of them. Take the average. That's going to be the prediction of y. Right? So I plot that blue guy. So that's a blue line. Right? Okay. So test error. Where's the test error? Test error is much larger than the training error. Never mind. So that's k being 15. That's a good situation. Let's see the overfitting situation with k equal to 1. I mean, just quickly. Remember this? We mentioned this is about memorization. We just have a function connecting all the dots. That's our extreme case of overfitting. And then we apply this function onto the same set of dots. We'll get a perfect fit and have no noise. Okay? We can do that out of sample. Training error will be 0. Okay? This is 0 for this guy. Out of sample, let's see. Out of sample is bad because we are memorizing the previous 100 points and now applying that to this 50. That's going to be bad. Now you can compare this. Test error for model 1 is 8. Test error for model 15 is 6. That's a lot of error. So we can also do 50. Same thing, just quickly. 50, you see everybody on this interval will get the same prediction because you're taking 50 neighbors. That's all the 50. So everybody here share the same 50 neighbors, and they'll have the same prediction. Right? Only when you move slightly inside, get a different thing. And and the error is even larger. This is training. Why I don't have a test here? Don't remember. Okay, that's the outcome after I have done the following part, finding the optimal k. Right? The way to find the optimal k is really, think about the previous code. We have done so many runs, but we just changed the k number. We just copy and paste the same code. Right? So why not just have a big loop, try all the possible k, repeat the same thing. And so that's what I'm going to do. I have a bunch of candidates for k from 1 to 30. So I just run a big loop. For each loop, I want to train the model and measure the mean squared error for training and test. Right? I want to plot the picture we just seen in the slide. So let me just do that. There's nothing new, right? We just encapsulate everything in a big loop. So the optimal k in this case, what? 3? That's the final thing. Okay? Training error goes to 0. Test error go crazy. And the optimal is 3. Right? So the main message is the same as before, right? So we have to replicate everything early. So my question, the good thing about simulation is you can change your seed and run the whole thing again, because we really want to say something about the fluctuations. We say, let's repeat the whole thing again. Let's see how much is the fluctuation. Here the optimal is 3. Right? Let's do everything again. Let me just go back. This is quick. I'm just commenting out the seed so that it doesn't take the same thing. Run again. Done. What do we learn? What do we learn here? I didn't change anything, right? So that single run we did in the first round is not that trustworthy, right? We run again, we get a very different conclusion. Now the optimal k is around 9 or 8. And you can see there's an irreducible error I plotted there, right? And this irreducible error in this case is basically the size of the sigma, right? It's 4. So you can see that actually the test error even go below the irreducible error. Right? There's something random going on. You happen to have a nice test data set, just match your prediction out of no reason. You just happen to be lucky. Right? That's possible because there's so many randomness going on. Right? Training error goes to 0. But the conclusion about k is very different. That's a problematic, right? So we try again. What? Now it's 17. Okay. So only by doing simulation we can see that, right? If it's a real data set, we run it once. We happily take 3 and go home. We get a good solution there. Right? Only by doing simulation we can see what we are dealing with. This is hard to reproduce in practice, but in the context of simulation, you can run it many times, take an average. Right? That's an easy thing. If you have randomness, the easiest kind of treat is run many times and take average. Yes?
Just want to know, in this case, what is the irreducible error? Is it 4?
Yeah, 4. That's the epsilon. Think about the f. So we generate a curved f. Then on top of this curved true f, we add the epsilon. The epsilon, the standard deviation of the epsilon is 2, I think. So that's the irreducible. This is the sigma square. That's it.
Why the k is the lowest distribution of the blue line?
Because at the end of the day, we want to find a k to give us the lowest out of sample error. right? This is the test error. The blue one is the test error. So we want to choose the model, give us the best test error. And yeah, if you trust this line, then it should be 17, right? But yeah, there's some randomness going on and all this. So in general, people say we need to figure out the randomness in a way. Later we'll talk about how do we figure out this randomness, even if you only have one data set. How do we do that? Just a way to do that, a very smart way. And if we can generate new data samples without having access to the population, now we can generate many data samples and repeat this whole thing and plot the variance. If we can plot the variance, we can say, yeah, roughly all these guys, actually, they're not very different. Sometimes you are the best, sometimes I'm the best. So in that sense, we choose the larger K, just to be inflexible. Yes. Yeah, there's a smarter way of doing that. Now, are we okay? Now back to the earlier question, what would happen if instead of having 100 data points, now I have 1,000 data points? That's also the beauty of simulation. I just need to change one number. 1,000, 1,000. Two numbers, sorry. How about test? Let me make test 500. All right? Can you imagine what's going to happen? Are we going to stick to the same K? That's right. What do we have? First of all, the zigzag thing is reduced because we have larger samples. It's much smoother, right? Close to the theoretical value, the irreducible error, everything, right? When the data sample goes bigger, we have less. We are subject to less randomness of the data sample. And earlier we say our optimal K was 3, was 8, was 17. But now it seems to be 30. Or even higher. Right? We didn't try. I should try that. Let's try 300. Crazy. Take some time. Some time to think. Uh-oh. Too big? There's a 30 here. I'm assuming 30 here. Stupid. There's too many points. We don't really need to do 30 actually. But we lose the point. Right? Let me shrink the x-axis a little bit. Up to 50 is good enough. Right? 100. Why can I not do this? 100 is good enough. Maybe 50 is good enough. All right. So what's the optimal? Beyond 30, 40, they're all pretty much the same, right? Why? Why earlier was around 10, now it's around 40? Why? Yes. Then? Good. Yeah, roughly that's the point, right? Think about it. Earlier you only have these several data points. You say, I'm taking 3 neighbors. I'm taking this whole range. In this big range, there are only 3 neighbors. Now I have data points everywhere. I still take 3 neighbors. I'm taking 3 tiny neighbor, right? So when we have data point anywhere, by taking small number, we are only covering a small range, right? But when we have a sparse data set, 3 neighbors means a big range, right? That makes a huge difference. And that difference is also more obvious when we plot the data set. What? That's 1,000? That's 1,000 data points. Think about it, when you take 10 neighbors, you're basically taking a tiny band, right? It's not like 10 neighbors earlier was big band, right? So we need to proportionally increase the K when the data is different. Okay? All right, so that's the regression part. Let me undo my changes. Okay. All right? Good. Now let's do the crazy one. This is the data set we are going to see again and again and again. In the future, every time we learn a new tool that can do classification, we'll come to this data set, apply that to this data set. And towards the end, lecture 12, at the end of the semester, we'll post all the pictures together and see this is a linear regression on top of this thing. This is a k-nearest neighbor on top of this thing. You can see all the difference, right? The same data set, but we want to have a very side-to-side comparison of all the tools. But this data is a bit crazy, and it's designed to be crazy, so that you can see the power of all these complicated tools. So it takes some time to digest. So the mechanical part is not very different, but the time to understand the data takes a lot of time. The data has a web page. I should have that. I have it here. No, not this guy. So it has a web page explaining what's going on. I'll come back to that later. But it's a data set made by simulation. It's not a real data set. It's simulated by design, and to be designed to be an ugly one. It's in the package of the reference book, Element of Statistical Learning. Also, there's the data called mixture example. Actually, it has some description, but really not meaningful. Let me try to explain. But first of all, inside this data set is a big list of many things. And let me pull out all these things first. So there's a X, Y, prop, X new, all these things. First, what is X and Y? So X and Y are the training data, two-dimensional. X1, X2, again for the positions, and there's some colors, some other things. Yeah, these are the ones, right? These are the Y's. For 1, this for 2. Right? That's the same thing, right? But the bad thing about this is these points are not coming from two multivariate normal. All the circles coming from 10 different families. So if you have 2 earlier, we said you can find a straight line to cut through, to split the 2. But you have your 10 different things here, and there's another 10 for the other family. The boundary is going to be curved like a crazy. So it's very hard to figure out the underlying thing. And the task for us is to find the boundary. Just like in the early example, we want to find a boundary like that. Let me not get into the underlying 10 families, but let's think about the simulation part. The simulation is really done like this. There are another, so that's the training data. Let me talk about the grid. So we also have the population, that's the grid. So just like earlier in the slides, we have a pretty dense grid, like this, many things. So it's prepared for us in the package. This is called PX1. So that means the same X1, but PX1 is a vector of the ticks. What's this point? What's this point? So they're like number 1 to number 69, I think. 69. yeah, 69. The 69 vertical lines on the x1 axis. There's a px2 that is 99 vertical lines, number 1 to 99. So in total, it's a 69 by 99 super dense grid with all these points are the 6,831 points on this grid. Okay. So later, in order to plot the boundary, we will predict on this whole grid of 6,000 points. So we're using this model, choose a k, that's going to be a model, and we apply that to the whole grid. Right? The same story. But then we say, where's the true boundary? The true boundary, let me plot the true boundary first. Let's ignore this guy. Let me plot the true boundary. That's the sample data. That's this guy. Okay? I have some red, some green, and they're all deeply mixed together. But even they're deeply mixed together, there's some area that's more red, there's some area that's more green, right? And not evenly mixed. So there's some kind of a way to separate them. And the true boundary is in the data. This is, let me plot it first and let me explain. So that's a true boundary. True boundary of separating. Things on top is more likely to be red with larger than 0.5 probability. Things on the bottom is more likely to be green, less than 0.5 probability of being 1. Right? That's a true boundary. So how do they get a true boundary is based on the 10 different families here and 10 different families here. We said when there's 10, the boundary is not linear. But that's not important for now. The important thing is how do we draw this thing is really based on the probability guy given to us. So this one term called the probability. So that's basically tell us on this whole grid of 6,000 something points, every point has a probability of being 1, or being red. Every point has a probability of being red, say 0.75. This is the guy. I said some guy at the bottom is more likely to be green. This one probability of being red is 0.2. Right? So at any place, there's a given probability in that big vector. And the true boundary we are getting, something like this, is the boundary that points on this boundary is exactly 0.5. So that's exactly, it's hard to differentiate. On one side it's higher, on the other side it's lower. Right? And that's a bit hard to visualize, but really the probability is a 3D surface defined on this grid. It's a 3D surface. And the probability goes from 0 to 1. This is a 3D surface. And what we want is this boundary is to slice that 3D surface at exactly 0.5. So this is 0 to 1. We want to cut that at the 0.5 level and get the cut, the contour. That's exactly. The 3D surface is this guy you have seen. That's the true probability F plot. There's a px1, there's a px2, and the height is the probability. Right? That's that 3D ugly thing. Right? Don't worry about that. And our task is to find the 0.5 cut somewhere at 0.5. Where is 0.5? Z to be 0.5. When the height is 0.5, we cut it off and see what's the shape there. So that's the boundary. Right? So on one side is more, on the other side is less. Right? So that's the true ones. And we have plotted the true ones. And later what we do is we would use this model to predict on every individual point here, 6,000 of them. Then for each of them, we are also going to predict the probability. Now, when we do the prediction, we don't know the true probability. We are predicting one based on the votes from the neighbors. So every point we have a true, predicted probability. Then we can apply the same technique, draw the boundary according to the prediction. Okay? Then we can compare the true ones and the implied ones from the model. Right? So if that's somewhat confusing, that's basically this guy. That's basically the same thing. Right? There are two lines. The dash one is the true one according to the data generating model. And there's a solid one that is predicted by your k-nearest neighbor. Okay? On each point, you have a probability prediction. Let's just find the 0.5 cuts. Okay? Same idea. It's just more complicated in the data. Let me see what else I need to explain in the data. Not much. We are only going to use this probability. So that's a visualization of the true thing. Let's leave it on the side. Now we can do k-nearest neighbor. The k-nearest neighbor part is pretty much the same, but now we are doing classification. Earlier was KNN.reg, regression. Now it's classification. So you need a little bit extra effort to read the documentation. Same thing, you need the training X, the test X you want to predict, and the class. Class is basically the Y. That's the label. And the K, and yeah, here is actually default is 1. That's all difference. Probability is when you predict on one of the new points, do you want to have 0, 1 by majority vote, or do you want the proportion to be returned as the probability? Right? Earlier we said we have two situations. Here, since we are drawing this, we need the probability. So we need to specify we actually want the probability. The rest are the same. We good? So let me just run that with K being 15. X is this 200 points, and the X new is all these guys. That's all this. So I've already processed all those things. The other ugly part, you need to find it out from this buried somewhere deep in the documentation is, I ask for the probability for a point, but it doesn't give me the probability of being 1, this ugly package. It gives me the probability of the winning class. Right? So you have 15 neighbors. They were all 15 are zeros. So you label this guy as 0, and you want the probability. It tells you 100%. 100% of the winning is the proportion of the winning class. 0 wins in the majority vote. But what I really want is 0% because I want the probability of 1. So I have to do some tiny fix. But that's the probability. So we pull out the probability, and we need to fix that. So if the winning class is 1, we just keep the probability. If the winning class is 0, that's otherwise, we just use 1 minus. Right? To flip that. Right? That's the probability. Now we can plot. Other plots are the same thing. Now we have this thicker blue line. So that's the boundary for the k-nearest neighbor with 15 neighbors. That's the 0.5 slice. Right? There's also an ugly surface for the probability, but that's a slice at 0.5 level. And we need to measure the training error. Why do we need to measure training error? Yeah, earlier we were in the previous file, we do the stupid version first, predict on the training data, then we do the regular version, predict on the test data. Here we do the opposite way. And the first time we run that, we are predicting on the out of sample data. Right? That's the one we want. I don't know, here probably I just want to show you the training error is weird. So if we want to get the training error, we need to run that again with the to predict on the training data. And the output, this is run the k-nearest neighbor again, and the output will be 0, 1 on each of the points. And another ugly thing is the output, even this 1 is a character, not a numerical value. So we need to convert that to numerical value. There's a lot of mines out there. Then we can count the error. What do we mean by error, training error? That is how many times your predicted y is not equal to the true y, right? How many times that the sum of the situation they're not equal. That's 31. That's not a ratio, so we need to use that 31 divided by the total number of points. That becomes a training error, 15.5%. Right? Out of 200 points, we have 31 errors. So that's training error. We don't have test error yet. Let me do that later. But let me quickly run for k equal to 1. You can imagine what's going to happen. Right? There's a lot of islands, 4 dots, green dots, deep in the enemy's home. Training error, 0. We should know that. For k equal to 100, that's an inflexible version. We know what's going on here. Training error should be bad. Not worry about it. So now it's a test error. Earlier we said we can measure the error on this big dense grid, but that's not what the regular way of doing that. The better way is, since we're doing simulation, why not simulate a new data set? Yeah? So we're simulating a new test data set, and that involves all the 10 families here, 10 families there. So assume it's working. Right? This is just a piece of code from the textbook, having all the 10 centers and generates the bivariate normal. Let's not worry about that. Now we have a test data set. Magically, that we run the big loop to see the out of sample error. It takes a little bit of time because the sizes. So the majority of the code is the same as before, right? It's just taking a different data and using some classification. When we do classification, there's some little tiny details about the probability of a winning class versus the probability of 1, all these things. So what is optimal k? 7. Let me plot everything. I have the irreducible error. So that's the final picture for today. Again, the same pattern. Pretty much everything is the same. But we actually find out the optimal is 7. And if we want to do the optimal one, we go back and check 7. We'll save that picture for the future. Let me make it 7. That's the only number I need to change, probably. With 7 neighbors, it almost perfectly captures the truth. Right? There's some overfitting on the side, but almost perfectly captures it. With 15 neighbors, earlier we have seen on the left side it's okay, but on the right side it doesn't capture this cut because you need 15 neighbors and there are not many points here. Right? With 7, you nicely capture that. Right? This is pretty much the best among all the tools we're going to see. Right? But this is really the nicest situation for k-nearest neighbor, 2 continuous dimensions, easy thing. Right? But this is we claim this is the worst tool, but at the end of the day, you will see that works the best for this example. That's the best situation for us. Okay. Further questions? So we're done with this. for today, homework. Have a homework. You have 2 weeks. Next week we don't have class. Right? You have 2 weeks. Next week is a public holiday. No class. So I'll give you more homework to work on. That's it. So the first thing is to learn R Markdown. I think if you know R already, it's half an hour of work. So I have the template for you on the IVLE. Where's my IVLE? So I have the R simulation. The one I have showed you is the output HTML file. This is a web page. And the source code is here, RMD. You can check inside and see how to do that. If you're really lazy, just delete all the content and add your own stuff in there. So in the future, all the homework will be in this format. Give me both files. Yeah. This is half an hour of work. I have a tutorial link here. And there's a cheat sheet. Yeah. And the next one is to test the curse of dimensionality. When we go beyond 2 dimensions, the performance of a k-nearest neighbor go down significantly. So that's the homework. So you need to simulate data. I'll give you a piece of sample code for simulating 2. Then you will have the third one, fourth one, fifth one add into this data set, and you will see the performance decreasing. The key point there is when we add x3 here, x3 is some irrelevant x. Only x1, x2 are relevant. We first get this model, then we add another x3 that has nothing to do with this one. But when you do k-nearest neighbor, you don't know, right? This x3, now you have 3 dimensions. Then when you do k-nearest neighbor, so you're basically lifting these points from a flat surface to a 3D place. They're everywhere. All right, you're finding the next. Then you have an x4. I don't know how to imagine, and all the way to x20. And because they are irrelevant, if you have a reasonable model with some capability of model selection, they will identify these are irrelevant. We delete them. We are fine. But k-nearest neighbor doesn't know how to control that, so it will just use all the x to measure the distance and mess up many things. Right. So I'll give you some descriptions in the R Markdown format. You can fill in the code in the template and your explanations. That's also the format of the test. I'll give you a template already. Yeah. Okay. And next week we move on to some more serious tools. But next week we'll most likely only have time to cover the classic side of the linear regression. We'll spend most of the time criticizing the classic things. Right? So we have been talking about the in-sample, out-of-sample. Right? Think about the linear regression. If you ever learn anything, there's nothing out-of-sample. Everything is in-sample. There's nothing meaningful out there. R square is in-sample. Right? P-value is also in-sample. Right? Okay. Good. Right on time.